Yeah, and so now we're on again. Okay, so let's go back and take a look at that formula that we just had, which was F equals QVB sine theta. Now, one thing I left off of this formula is that F is a vector, and B is a vector, and V is a vector. And so those are all vector quantities. And so while we saw this, it's easy to figure out what the magnitude of F is. What we did not talk about is the direction of F. And to figure out the direction of F, we're going to use something called the right-hand rule. And there are different versions of the right-hand rule. And depending on who teaches you and where you look, you'll see different ways to find these. So I'm going to teach you the way that I do it, and you are welcome to look on the internet and find other ways. But as we go through this stuff today, we're going to use different types of the right-hand rule. So we'll start with, we'll have a moving charge going in this direction, and we'll make it a positive charge. Remember, we always usually define things in terms of a positive charge. That means if instead of a positive charge you have a negative charge, you have to take your answer and reverse it. And so we'll have a positive charge moving in this direction, and I'll have a magnetic field going up. So there's B. And I want to figure out the direction of the force. So I'm going to put my hand in front of the camera, even though I can't actually see the camera. None of these. Nope. Nope. Okay, so I'll just try it and see. Okay, so what you do is you put your fingers in the direction of the velocity. Put your fingers in the direction of the velocity. So you're pointing in the direction of the velocity. And then you need to curl your fingers in the direction of the magnetic field. And often that means you'll have to rotate your hand in some sort of way, because our magnetic field is going towards the top of the page. And so now I curl my fingers in the direction of the magnetic field, and I look at my thumb. My thumb is pointing out of the page, and so that means the force is coming out of the page in this direction. So for this particular example, whoops, F direction. Out of page. Okay, so let's try another example. Let's say we have a magnetic field. What direction is this magnetic field? It's going into the page. And I'm going to have, just to throw things for a loop, I'm going to have a negative charge moving in this direction. Now what I recommend is you do things exactly the same way, and then you just flip it at the end. Other people will tell you other things, but they are wrong, and my way of doing things is the best way, even though other ways are just fine. So you hold your fingers in the direction that the charge is moving, and then you figure out how to rotate your hand so that you can curl in the direction of the magnetic field. And then, so this way, and then I curl this way. My thumb is pointing up towards the top of the page. And so the direction, did you not get that?
I don't know. I was watching you and then
okay.
So like your page is like this.
Oh, my page is vertical. Like, yeah. Okay, so I'll do this and then yeah. So yeah.
We got it.
Okay, so I'll do this and then you do it on your own. So point your fingers in the direction of the moving charge, curl towards the direction of the magnetic field, and your thumb should be pointing towards the top of the page. Okay. Okay, I'll come around and help each of you.
She's using her left hand.
Oh, yeah, the left-hand rule will get it backwards. Okay, so except I made a mistake. The force is not towards the top of the page because it's a negative charge.
So you could use your left hand for negative
Yeah,
charges.
some people do that, and I don't go that way.
I like that.
Okay, so since my thumb is pointing towards the top of the page, but it's a negative charge, then the force is towards the bottom of the page.
How you managed
To try to draw the mouse.
I did that last time. Okay, so I'm going to pause it and go around and
I'm like,
have
wait,
you
this
all.
is the opposite direction of what everyone else is getting.
Yeah, because it looks like you were doing it just right. Avogadro says this is completely unfair. Here is our problem. So you might want to, I'll try to write down the important stuff too. Okay, so we have an electron, so that's important. We need to know what kind of charge we have. So we have an electron. It is moving perpendicular to a 1.0 Tesla field. The electron has a velocity of 1 times 10 to the 7th meters per second. And the question is, what is the magnitude of the force? It's a pretty straightforward question. So what was the charge on the electron?
1.6 times 10 to the negative 19.
In units?
That was crazy.
Units?
Coulombs.
Coulombs.
Yeah.
Wow.
I'm only looking for magnitude, so it doesn't matter.
That's right. But still it is negative.
No, because
Well,
it's
we're just
magnitude.
looking for magnitude.
Okay.
Yeah. Okay, so what did we get?
1.6 times 10 to the negative 12.
And what are the units?
They're in
It's a
newtons.
force, so
They're
it's
in
newtons. It's newtons.
And
Okay,
then I both.
now let's take a look at this situation again. So where we have a moving charge that's moving perpendicular to a magnetic field. Now, as long as this electron is moving within the plane of the page, or proton, doesn't matter, let's just make an electron. As long as it's moving within the plane of the page, will it still be perpendicular to this magnetic field? Does it matter if it's moving in this, this direction, that's supposed to be a straight line, or this direction, or this direction? Is that still going to be perpendicular to the magnetic field?
Yes.
Yes.
Yeah, it still will be. So in all of these cases, it's moving perpendicular. Okay, but let's look at what happens. Oh, I need to make that smaller. That's a little too small. Okay, so let's look at what happens in this particular example as it moves into this magnetic field. So it moves into this magnetic field. What direction is the force? Oh, the force on the electron,
Oh, the
not the
force.
magnetic field, the
Down.
force on the electron,
Oh.
towards the bottom of the page. Now, as the electron moves in, is it immediately going to say, okay, I'm going to start moving down now because of that force?
No.
No, because it already has a velocity this direction. As a velocity this direction, it has a force down, so it's going to move a little bit this way. Now, once it's moving this way, what direction is the force on that charge? So let's think about it. We've got, put your fingers in the direction of the velocity, and then curl in, and your thumb is kind of pointing in the northeast direction, but it's an electron, so it'll be pointing kind of in the southwest direction. So then it'll feel a force that's pushing it kind of this way.
So it will essentially go in circles.
Yeah, it's actually not essentially, it will. It will move in a circle. And we kind of know that because of the fact that the force is perpendicular to the direction of motion. Whenever the force is perpendicular to the direction of motion, we have a centripetal force, and it will move in a circle. So we know that if it's a centripetal force, we know that centripetal force is mv squared over r. And it's going to move in a circle because v is constant, because the force can't affect the magnitude of v is constant. The force cannot change the speed of the electron because the force is always perpendicular to the motion of the electron. So the force has no component in the direction of the velocity. So it can't change its speed, it can only change its direction. So the centripetal force is mv squared over r, and then that has to equal the force from the magnetic field, which will be qvb. And so you can use this formula if it comes up and the question asks you something like, what is the radius of the circle? or whatever, but you also have to know the mass of the electron for that.
What is the mass of an electron?
Mass of an electron. I'm terrible with constants.
9.11 times 10 to the negative 31st.
9.11 times 10 to the negative 31st.
Kilograms.
Okay, so as long as we already have this problem here, let's figure out what the radius of this circle would be. So tell me the mass again.
9.11.
9.11 times 10 to the negative 31st kilogram.
Now, I'll probably end up putting this on YouTube because it's the easiest way to store videos. And then people will say, who is this person who's trying to teach this stuff who doesn't know these fundamental constants? And I'll just say, there's no need. I just can't remember them. I just can't.
You can look them up.
You can look them up, but I should.
I
Okay.
think it is 5.694 times 10 to the minus fifth.
Probably.
Not
Six.
dealing with sig figs.
94 times 10 to the minus, what'd you say?
Fifth.
Fifth.
I think
Meters.
that's
Let's see if anybody else gets the same thing.